Hello guys, welcome to the next bunch of tutorials wherein which we will be continuing our discussion. So in the earlier bunch of tutorials we looked at two important things. Now one is we understood the basic constructs of Python, and then we looked at implementing the ideas of basic regression and then CNNs and stuff using NumPy. Now we shall move into a very important library which is PyTorch. These sets of tutorials are designed in a way. First we will understand the basic functionalities of PyTorch, and then we will go ahead and implement the basic models like linear models, so and then MLPs, and then we will implement CNNs, RNNs, LSTMs and stuff. And then in the next section we will be looking into the idea of loading the pre-trained models and how you can modify the networks for your downstream tasks. This is how we have structured this whole section of tutorials, in which we will have multiple tutorials. So in that, as the first one, let us proceed with understanding the basics of PyTorch. Now couple of important libraries that are needed while going ahead and implementing PyTorch. As you can see here, one is the base library which is torch. Now this is in line number 5, which you can see is import torch. Now this is the base library, and then you want to go ahead and work with the neural networks. Okay, so you want to go ahead and declare, or you want to define a CNN, or if you want to define a transformer model. So then now we go ahead with this NN, and then so different kind of optimizers you want to use. Then we need this torch.optim as optim, and then if you want to go ahead with all these activation functions, then we will be using this functional torch NN functional, so as F. Okay. Now what is the version that we are using? So if you want to look at the version, it is the version that we are currently using is 2110. This is the version that we are using. And whenever we are using PyTorch, another important thing that needs to be noted is the availability of GPU. Now we all know that the reason why we do not use lists or NumPy array is they are designed to work on CPU. We need data structures that are designed to work on GPUs, accelerator devices. So now you might have GPU cards. If not, we can use freely available cards from multiple sources. Now one such source is Google Colab. Now you can go to this runtime here, and then you can look at here and click on this change runtime. Now you have CPU, which is the standard thing that is available, or you can use this hardware accelerator T4 GPU, or you can use this TPU. Okay. Preferably for most of our working, we will be using this T4 GPU, which does not cost us anything, but it is allocated based on the availability and your usage for sure. So now you can save this. If it is CPU, you can make it as GPU, and then you can save this. Okay. Now how do you check the availability of GPU? So now here torch.device, now CUDA, if torch.CUDA is available, now this will check whether any accelerator is available. Okay. So else if the accelerator is not available, we will be using the CPU. Now when I print it, okay, now we will be able to see the device. Now as of now we have using the CUDA device, so you can see it here using device CUDA. Okay, we are using Tesla T4 cards. Okay, so you can get the names of it. Okay. So now, so just because we are coding in Google Colab, that does not mean that every time the GPU has to be enabled. Okay. Now the way in which normally you can do is you can write every of your code initially, do a sanity run, and then you can enable the CPU, so you can disable the CPU and enable the GPU, and then you can rerun it, so that the allocated time will be reduced. Okay. So now similar to what we saw in NumPy, now let us create some tensors. Now if you have a list, now you can go ahead with torch.tensor and then you can create from a list, you can create a tensor torch.tensor for this. Now this is your y. Similarly you can create a matrix, so on and so forth. Okay, this is from a list. Okay, yeah. Now what are the attributes? The attributes that are available are, now first here I am creating a torch.randan. Okay, so here I am sampling from the normal distribution. So I am creating a tensor which is of shape 3 cross 4. Okay, this is what you are specifying. Here you are specifying the shape of it. Okay, so now then I am printing the tensor. Now x dot, so that x is its tensor. Now it has attributes like shape, what is the data type and where is it. So whenever any given tensor is created, now it will be by default will be on the CPU. You have to explicitly port it onto the GPU. Now down the line, now we will see how to do so. So that is the reason you can see it here. Whenever I check the attribute x dot device, now you can see in the output that it is there on the CPU. Okay, now data type, now what is the shape, and then the, so you can see that now this shape which is there is in, you can get what is a shape of 0, what is shape of 1. Now you can get it and then know what is the how many rows are there, how many columns are there, you can fetch it like that. Okay. Now this is a random, so sometimes we might need some special tensors. Okay, sometimes you might want all the elements of the tensors to be 0, sometimes you want them all ones, sometimes you want it from a specific distribution. So let us say that here you want it from a uniform distribution or from a normal distribution, or you want your tensor to be an identity matrix. So like this, depending on the need, we might need to create some special tensors, and then we have the necessary ways of doing it. Now if you want all zeros, now torch.zeros, you specify the shape. Now in what shape? You want in 3 cross 4, now you specify it. So ones, if you want all the ones, you specify 2 cross 5 here. Now if it is uniform, okay, uniform 0 1, so you can use just torch.rand 3 cross 3, the 3 cross 3 tensor, now wherein which each of the value is sampled from a uniform distribution. Now this is a normal distribution, sampled from a normal distribution similarly, and then you have an identity matrix. So identity matrix of size 4 cross 4. Okay, identity matrix is only defined for a square matrix, so therefore specifying one of the shape is more than enough. So once I run this, now you can see that all zeros which is of shape 3 cross 4, whatever you have defined here, all ones which is 2 cross 5, so a 3 cross 3 uniform tensor, a 3 cross 3 normal tensor, and the 4 cross 4 identity matrix. Okay. Now this is how you can create the tensor of necessary details. Now then indexing of a tensor. See, indexing is similar to what we looked in the list or in NumPy array that we have. Okay. Now if you have a tensor x which has been created from this list, okay, now you can go ahead with accessing the 0th element, or if you want the last element, or you can slice it. The same old things are available. Now you can look into it. The same thing works with a 2D tensor as well. Now you have a matrix, this is a matrix, and then you can access a specific element, you can access the first row, first column, okay, and you can take a specific suction of a matrix. Now as we have done, this example is similar to what we saw in NumPy, but using tensor. There we used a NumPy ND array, here we are going ahead and using a tensor. That is a major difference. Okay. So now let us look into a very important feature that is needed for us is I have a tensor of some specific shape. Now I want to change the shape of the tensor. Okay. Now you can take off a straightforward example that you have extracted the feature in a CNN and then you want to flatten it out now for going ahead and putting into a classification head, or you have used an MLP, you want to resize it into a matrix. So depending on variety of applications that you have, you can go ahead. Now I have a tensor which is torch.arrange 12. Now this gives me from 0 to 11. So this can be used even for if you want to create some kind of indices, so it can be used, this functionality. So torch dot arrange of 12. So the original tensor, which is there x, and then the shape of it is it has 12 elements. Now I am reshaping it to 3 cross 4. Now please remember that you cannot reshape it to 3 cross 5, you do not have such elements. So it has to be compatible. Now that compatibility you should be looking into. So then because of that you have reshaped it. So the first 4 elements 0, 1, 2, 3 will becomes the row, so it goes on filling row wise. Okay. So therefore whatever you have converted it into a 3 cross 4 matrix. So what was elements which are arranged, you have converted into a 3 cross 4 matrix. So now sometimes we might want to do it in some other way. So now this is one way, reshape is one way. Now we have another way which is view. Okay. So normally you can use either of them. The main difference is in terms of memory allocation. See, view needs the memory to be allocated in a continuous manner, but reshape needs a non-continuous memory allocation works well. But going out of those nuances, now both of them perform the same thing. Okay, you have till 12, either you can give x dot view and reshape it to 3 cross 4, or you can use x dot reshape. Both of them perform the similar operation, but only what do you call, the devil lies in the details. Okay, now you can go ahead with that. Now this is, you have some numbers, so you want to reshape it. Now sometimes you want to add a dimension. Okay, see, if you look at here, x which is there, now it is has 12 elements, so you can see it here from the original shape it is 12. Okay. Now what if I want to convert it into 1 cross 12 or 1 cross 1 cross 12? Now sometimes during the shape manipulation we might need these kinds of functionalities down the lines, whether in CNNs or in RNNs and stuff. So now how do we do it? Now we can use what is known as unsqueeze and squeeze. Okay. Now this unsqueeze functionality which is there, it will add a dimension, and squeeze functionality which is there, it will remove the dimension. Okay. So now let us say that I have a tensor which is having the values 1, 2 and 3. So the size of this will be 3. Okay. That is what you can see here, the original size here, and then x dot unsqueeze 0. So that means that you insert a dimension at the index 0. So now because of which, now if I go ahead with this unsqueezed shape, now you can see it here, now it is 1 cross 3. Okay. Now if you want to make it 3 cross 1, now that is also fine. So then you want to squeeze it in the dimension 1. So 0, 1, so always counting start with 0. Okay. So it becomes 3 cross 1. So now you can take either of them, and then if you perform the squeezing, okay, so whatever was unsqueezed for which you have added a dimension, that will be removed, and then you get the value like this. So therefore depending on your requirement, either you can add dimension or you can remove dimension. Now this will be very much useful for us going ahead. Okay. Now another important functionalities that is needed for us is changing the order of dimension. Okay. See, what happens is most of the times if we take an image, now preferably we say that it is height cross width cross channels, but whenever we are going ahead with implementation, we might want the channels, now which is the third dimension. Now if you consider the dimension, so now if you take it like this is 224, 224, 3, okay. Now this is of 0, 1, 2, but sometimes we might need 3, 224, 224. Now in that case, now we need to permute the dimension, okay, without modifying the content. Okay, we need to permute the dimension. Now how do we do it is what we are looking into. So now I have just taken a random tensor which is of shape 224, 224, 3. Now I think you remember this 224 cross 3. This is the standard size that we use in most of our ImageNet images. Okay. So then you have the shape 224 cross 3. Now you want to permute. Okay. The first will be 220. So the first will be the second one. Now which is 0, 1, 2. So 3 will be the first one, and then 0, 1. So this 224, this 224. Okay. So now what I did, so it's like I want the second index to be then 0 and 1. Now this is how I am permuting it. Okay. So now whatever is here is coming here, this coming here, and this coming here. Okay. This is the idea of permutation of the dimension, change the order of the dimension. Okay. So now let us look into some of the very basic tensor operations. Now the standard addition, subtraction, multiplication, division, exponentation, so which is similar to the NumPy operations that we have already seen. Now we can look into it, and then so we can look at the matrix multiplication, which is a very important operation that is needed. If I have matrix A and B, which is of in this case which is of the same size 2 cross 2, 2 cross 2, you can use this at. Okay, similar to what we used in NumPy, you can use this at, and then you can go ahead with the matrix multiplication. Okay. So this is regarding matrix multiplication. So then now coming to the important thing, as I told earlier, any tensor that is created will be there on the CPU. Okay. Now you want to port it, you want to move the tensor onto the GPU so that the operations can happen on the GPU. And one important thing to be remembered, that if you are performing any operation, all the necessary things should be there on the GPU. For example, if you are running a model, okay, now you need the forward pass, so you need X and Y. Now all these needed things has to be there on the GPU. Only subset of them being there on the GPU is not allowed. Okay. Now how do you do it? Now you can, this is a random tensor I am creating. So x dot device, now this is an attribute of the tensor. Now initially it is on the CPU. In line number 9, what is that I am doing is x dot to device. Okay. Now this device, so since the GPU is available, we have already enabled it, I am moving it onto the GPU. Okay. Now that is the reason when I use it post this porting, now we can see that it is there on the CUDA device. Okay. Now always whenever we want to perform any operations, all the needed things has to be there on the GPU. Okay. And sometimes if you have multiple GPU cards, it has to be there on the same GPU card. Okay. Now consider that you have a system wherein which you have 4 GPU cards, your model is on one GPU, your X is on another GPU, your Y is on another GPU, it will not work. Okay. All of them has to be there on the same GPU card, unless there are ways of doing it, but this is the standard procedure that we use. So now let us look at a very important idea which is needed for all of our models that we will be using. How does the gradients gets computed? Okay. Now the workhorse that we have is gradient descent. So we should know how does the gradients actually go ahead and work. So now here I have creating a tensor with only one element, which is 2, and then I am enabling require grad is equal to true. Okay. So now this will take care of tracking of the gradients. Okay. So now torch.tensor I am creating with value 2. So now the x that I have, okay, the x that I have is having the value 2. So now proceed. Now y, I am computing y, x square plus 3x plus 1. Okay, the y that I am computing is x square plus 3x plus 1. Okay. So now if I go ahead and compute the gradient of this y with respect to x. So now we will be going ahead and finding dy by dx at the given specific x is equal to 2. Now this will be 2x plus 3. If you substitute the value, now we will get 7. Okay. Now let us check that whether it is there. Now we just need to use this y dot backward. So now it will be able to compute the gradients with respect to the parameter which is there here, which is x, that is being used. So therefore you can see that the gradient which is dy by dx with respect to x is equal to 2, you can see that it is a tensor of 7. See, again I just want to emphasize another thing. See, if x and y, whenever they are on the same device, the gradients which will be there will also be on the same device. Now as of now the device that is there is CPU. I haven't ported anything onto the GPU. Okay. So now let us look into how does the same thing happens now whenever you have a tensor. So I had a scalar, so the same thing we are extending it to a vector. Now I have my x, now which is in this case, x which is there is x1, x2, x3, which is taking up the values which is 1, 2 and 3, which is 1, 2 and 3. So now and then what do? I perform y is equal to x square. So that is my y is, so x1 square, x2 square, x3 square. Okay. Now in this case this is 1, 4 and 9. Now this will be the content of my y. So now then what is the loss? See, here again I have declared requires grad is equal to true. Now what is the loss? The loss is y dot mean. Okay. So now this is now loss will be 1 over, there are 3 elements. So 1 plus 4 plus 9. Now this is 14 by 4. Okay. Sorry, 14 by 3. 4.667 around that will come. Okay. Now this is the loss. Okay, we have got the loss. Now let us go ahead and find now how does the gradient work. Okay. So now we have the loss. Now what is this loss which is there? Now this is 1 over 3 of y1 plus y2 plus y3. Now this is 1 over 3. Now what is y1? x1 square plus x2 square plus x3 square. Now if you go ahead and find the gradient with respect to what you are finding. Now let us say that you are finding the loss with respect to some xi. Now how it will be? So now this is xi of 1 over 3 whatever x1 square plus x2 square plus x3 square. Now if you use any specific xi, now let us say that I am going ahead with x1. Now then if you are going ahead when computing the loss with respect to x1, so the remaining things will be 0. So now this will be 1 over 3 2 into x1, which is 1 over 3 2 into 1, which is 2 by 3, which is 0.667. So now the gradient with respect to this for anything, so it will be having 3 elements. So it will be, okay, it's better to write as the x itself, x. So this is 0.667, this is 1.333, this is 2. Now this will be the gradient. So since it is we are doing it for the first time, I thought we will go ahead with the full fledged computation. Now we can see the same here 0.67, 1.33 and 2. Now this is the gradient computation that will happen. Okay. So now let us go ahead and perform a manual linear regression with AutoGrad so that we can understand how is things working. So now my x, now I have 1, 2, 3, 4. Now it is like see, now please remember this is the first example, second example, third example and fourth example. Okay. These are different examples that are there. Okay. So now and then my y is 3, 5, 7 and 9. Okay. So now the w, so now what is that we are trying to compute? Now y is equal to wx plus b. Okay. So that is what we are trying to look into. Okay. Now y equals wx plus b. So we want to, okay, now to be even more specific I can say that now we are going ahead with y hat. Okay, fine. So now the w that I need is a scalar, so I am going ahead with some random number which is requires the gradients. So and then b, which is the bias term, which is 1, the learning rate that I am going ahead with 0.01. So now you go ahead and perform. The first thing is for you just want to iterate for 100 times. So you are iterating over the whole of the data that you have. So as of now you have 4 elements. So x you are getting it as so x into w plus b. Okay, that is your prediction. Now here you are obtaining the mean squared error. So the difference you are taking the square of it, so that this becomes a positive entity, and then you are taking the mean of it. Loss dot backward. Now you will be able to compute the gradients. Okay. So now with respect w and b, so now then you are manually modifying it. Okay. See, normally we do not do this. So whenever I use this with torch.nograd, now that means that whatever is inside this block, now which is there, now here these 4 lines, for which in these 4 lines we are not going ahead with any gradient computation. So okay, so but now what we do is normally we take care of this automatically. Okay, here we only have 2 parameters, so we thought that okay, now rather than going ahead with updating it using a call, so we want to do it. So w is equal to w minus, so whatever is the learning rate, which is 0.01 into the gradient, so with respect to the w, again the same thing with respect to z with respect to b. And then what do you do is, see, this PyTorch has a natural way of accumulating gradients. So before going ahead with any kind of gradient updates, now it is needed for us to clear off the gradient. Now that is what is being done in line number 26 and line number 27. Okay. Now either you do it post updation, so that for the next iteration you do not have any gradients accumulated, or you do it at the beginning. So it is a design, it is a choice that you can go ahead and make it. Now here I am making it after the updation. So then after every 10 epoch, so I am going ahead and printing what is the loss, and then finally the learned weights that we have. Okay. So now we can see here over the things, now we see that the loss decreases. So this is a regression problem. So as the loss decreases, this is the final loss that we have. The parameters that were learnt, w is equal to 2.13 and the bias term is 0.609. Okay. So now this is how we do it manually. So now let us do the same thing now using the needed packages, okay, needed packages and module. So now we need to use what is this known as this nn dot module. Okay. Now we need to create a class now for the model. Okay. So and then whenever we are creating models in PyTorch, every model that we create has to be a child of this nn dot module. That is what you are specifying it here. Now this linear regression model which is there, now this is the child of this nn dot module, and in the init, now first you are calling the init of the parent, and then so you are creating a linear layer. So with nn dot linear is the functionality that we are using. Now this is what is the input and what is the output. So input is a scalar and output is also a scalar. See, now whenever we are declaring this, we should not think of so how many examples are there in batches. Okay. So every model that is being created is agnostic of the batch. Okay. Per example, what is the size is what needs to be looked into. Okay. Now for each example, the input, the x which is there is a scalar, and the output, the y which is there, which is also a scalar. So and then unless specified, there will always be a bias term. So therefore this declaration that you can see in line number 11 is exactly same as what we have done here. Okay. in line number 9 and 10 that we can see here. Okay. So now this is what we need to do it in the init method, and then post that we have to write this forward, okay, this forward method. So it takes x, so you just pass this x which is there through this linear layer that is there, which takes scalar as an input and gives scalar as an output. So that is the output. So this is exactly wx plus b when x is a scalar. Now how do we implement it? Okay, and then you create an instance of the model in line number 17, and then you can print this model. As you can see now here it says that the in feature is 1, the out feature is 1, and the bias is true. Okay. Now I think you agreed to my previous statement that is there always unless specified, now bias term will always be there. Okay. Now how do you go ahead with the training? Now you have your x that you have created, y that you have created. Now you do not need to create w and b as you did earlier in our manual case. No, we do not need to do that. Okay. So now you have this model which is there. Now you are creating an instance now of this linear regression model. So earlier we computed loss manually, now we do not need to do it, we can use the predefined losses. If you want to create some user specific losses, that also can be done. Okay. Now we will do it post in our discussions. So here the criteria that is there, this nn dot MSE loss, mean squared error loss, and then the optimizer that is being used is SGD. Okay, you can use SGD or Adam since it is a very straightforward and a small thing. So SGD is fairly comfortable. So now it is this updation which is there, you are using this stochastic gradient descent which is there for updating all the parameters that is there in the model. So model dot parameters will give you the list of all the parameters. Now again I just want to bring it to your notice in this case that in a model now you can have multiple subsets of parameters, now when which each parameter is updated by a different optimizer altogether. Okay, it is possible in the case, we will look at it when it is needed. Okay, so then a learning rate that we are using it 0.01. So first you go ahead with the prediction. Okay, so this is where wx plus b equation will be implemented, and then you compute the loss. Now to compute the loss you just need the prediction and then the true value. So since the loss you have already defined in line number 10 here that it will be an MSE loss, so the MSE loss will be computed. Okay, the first is optimizer dot zero grad. Now this is what I told you. So optimizer has the linkage for the parameters. So what you are doing is for each of the parameter that is coming under this specific optimizer, now whatever parameter is there you go ahead and make all the gradients as 0. Okay, in the previous step there are chances that the gradients can be accumulated. Okay, so we are just going and avoiding it, and then loss dot backward. So this is where we compute the gradients. So you have two parameters, one is w and b. For both of them the gradients will be computed with respect to w and b for the loss, and then optimizer dot step. Now this is where you update the parameters. This is where w is equal to w minus learning rate into the gradient which you have computed is implemented for all the parameters that is coming under that specific optimizer. Okay, so now that will be done, and then for each this is just the line number 23 and 24 are just for the sake of bookkeeping. Okay, now you can go ahead and see that. Now after 90 epochs the loss you have got is 0.0017. Now here, now whenever we did it manual, so after 90 epochs we got 0.027. Okay, so we are almost more than 10 times lesser. Now we can print these model parameters. Now what is the name of and the parameter, model dot named parameters, you can just print it. You can see this here that it is 2.03 and the bias is 0.9. Okay, now in our earlier case the ones that we have got is this is 2.13 and this is 0.6. We can see that now using these automatic differentiation that is using all this backward and optimizer dot step. Now we can have the cases in which there is a lesser loss, and then we go nearer to the actual weights that is there compared to doing it manually. Now this is the standard procedure. Now always please remember this. First you go ahead with the prediction, then you compute the loss, then you go ahead and make all the gradients as 0. So this line number 19 can be after line number 21 also. you fix the place where you want to clear off the previous gradients. So and then loss dot backward, now you go there and then here is the step in line number 20, now in which we obtain all the gradients for all the parameters with respect to all the parameters for this loss, and then optimizer dot step is where all the weights are updated. Okay. So now we looked at the parameters. Now let us bring in the idea of the batches. Okay. Now how to go ahead and work in terms of batches, and then you have multiple input features. Now previously also you had a bunch of examples, but the dimension of each of the feature was a scalar. Okay. So now here, now I have I am creating a linear layer nn dot linear, input feature is 4 and the output feature is 3. Now that means that so the input, each input that you are expecting is of size 4 and then that you are converting it into 3. So now what is this doing is, now we can think of this like the W matrix which is there is of R 4 cross 3. The X that you have obtained is R 5 cross 4. Okay. So now what do you do is this Wx plus B, this B will be having 4 elements. Okay. So or you can think of it as an augmented thing, that is perfectly fine. So this is W is okay. So better way of writing it is X W plus B, just to retain the shapes. Okay. So this is X is 5 cross 4 and this W is 4 cross 3 plus B. You have 5 examples, each of the examples were in 4 dimensional space. Now after this multiplication what you have done is you have transformed it, now you have got 5 cross 3, you have transformed it into a 3 dimensional space. Okay, fine. Now that is what this nn dot linear is doing. So you are creating a random vector which is of shape 5 cross 4, 5 examples wherein which each example is of shape 4. Okay. So and then so you just pass it through the linear layer, you get the output which is 5 cross 3. Now as the transformation that we have seen. Okay. So now this is fine. So now let us bring in non-linearities. Okay. Now again any neural networks without non-linearity is of no use for us, most of them. Okay. Yeah. So you have this tensor, I just want you to look into different non-linearities that are there. We will be looking at ReLU, we will be looking at sigmoid, we will be looking at tan H. Now these are the famous ones. There are others also, leaky ReLU, GLU, all those things. So we will, whenever needed, we will invoke them at the right times. So and then these activations are applied element wise, for each element it is applied. So whenever we go ahead, I am assuming that all of you are very much comfortable with the functionalities of ReLU, sigmoid and tan H. Okay. So this is how you get it, f dot ReLU, this is the functional that we have declared earlier if you remember. So you pass this X torch dot sigmoid, so of this X, and torch dot tan H of this X, just to understand that how the outputs are there. Now you can see that very easy to inspect is ReLU. So you can see that all the negative values are becoming 0. So these 2 values will become 0 and this 1 and 2 remains as it is, now as you can see here. Okay. And similarly the sigmoid and tan H will work. Now then how do you go ahead with converting the logits which are there into posteriors. Okay. So now for that we preferably use not preferably, we use softmax. Okay. Now we have this tensor which is 2, 1 and 0.1, that you are trying it to convert it into a softmax. Okay. So now this logits which is there, torch dot tensor. Okay. So and then f dot softmax for this logits across 1. Now what is this 1, along which dimension? Along the dimension 1. Okay. Now we have discussed what is 0th dimension, 1st dimension, 2nd dimension, so on and so forth. You are applying this softmax along the dimension 1. So you get this logits and then the posteriors. So and the that's how we get into probabilities, but in terms of any classification task from which I am looking into, so this is how you get P of y given x for that specific x. So and then it should, for sure it will satisfy the thing. So if you take the sum of it, it will be 1. Okay, f dot softmax is the one that is used. Okay. So now let us look into, we already looked into the MSE loss. Now let us look into the cross entropy loss. Okay, and please remember this thing. So the input for the cross entropy loss are logits. Okay, now but it is converted into probabilities inside of it, so we do not need to worry about it. Okay, so now you have these two examples. Now these are the logits. Now this is for the first example. Now this is for the second example. Okay, so and then these are the targets. The first example has to be classified as 0, the second example has to be classified as 1. So now you have 3 classes 0, 1, 2. Okay, so now let us look at it. Now then you use NN dot cross entropy loss, and then what is the criterion? So the criterion is this NN dot cross entropy loss, and we know that how it works. It takes the average of this. Okay, so minus log of the softmax conversion of this, and the minus log of softmax conversion of this value, which is there of the true class, is what is being looked into, and then the average is taken, that is the loss. Okay, loss will always be a scalar. So in line number 18 what is happening is, now you can see that loss dot item which is there. See now what happens is this loss which will be most of the times on the GPU. So you just want the numerical value of it, it will be a tensor, you just want the numerical value of it, you want to see in terms of the real value what is it. Now in that time we use this loss dot item to go ahead with that. Okay. So now the next very interesting idea that is needed is how do you create the custom data sets. Now here I just want to bring in a couple of ideas. See, most of the needed toy data sets that we use will be available publicly in the PyTorch repository. For example, you might have heard of this data set called as MNIST, you might have heard of another data set which is known as FMNIST, you might have heard of the data set which is CFAR10. Okay. Now MNIST and FMNIST are the grayscale data sets. Now CFAR10 is colored images which is of the smaller dimensional size. Now similarly you have lot of other data sets which is needed for different downstream tasks. So not only for classification, you have data sets which might be needed for other tasks as well. Okay. So that is available for us to work around to understand what is happening. But what happens is whenever we are working on real time applications, what happens is the data sets that we need for us to work may not be available publicly in the PyTorch repository. In those cases what do we need is we need to create a way of obtaining the data sets. Okay, we need to have a mechanism. So now what is needed is, now we want the data sets, so we want to put them into batches and so that we can iterate over it with mini batch stochastic gradient descent. That is the underlying idea that we want to use. Okay. So now let us create a very simple data set and then we will see how one is data set which has all the data ready, and then data loader is where we put in them into batches and then go ahead with it. Now let us see how it can be done. See, whenever we are creating a data set, now similarly whenever you create a neural network model, it has to be a child of NN dot module. Now similarly this also has to be a child of this data set. Okay. Now the simple data set is the name of the class, you can call it whichever thing you want. So this is the data set that you have. Okay. So then now it should have these three methods. Okay. Now one is this init, length and get item. Okay. In exact the naming convention has to be there. Now init is where, now whatever depending on the initializations that are needed you need to go ahead with that. Now length is a functionality, it is a method that will give you how many examples are there, and then to get one specific item and each element is indexed. So which indexed item are you going ahead and referencing is the question. Okay. So now here, since it is a very simple data set, I am creating some dummy data here. So on X I am creating 100 examples in which each example has 2 features. Okay, each example is a row. Okay, it is 100 cross 2 things. And then what will be the Y? The Y is you take the sum of this, the first column and then the second column which is there, or 0th column and then the first column which is there. Now if it is greater than 0 is what you are checking here. Now what do you mean by greater than 0? So it is a relational operation. The outcome of any relational operation which is there now will always be a Boolean value, and then when you convert that Boolean value either into an integer or into a float or into a long, now it will be converted. If the Boolean value is true, it will be converted into 1. Now if it is false, it will be converted into 0. So because of which you are creating Y, you are creating the labels wherein which if the sum of both the columns that are there, now if it is greater than 0, now then it is 1, else it is 0. That is the label that you are creating. Okay, fine. And then you have this length. So the length method which is there, which will return how many examples, the length of this. Okay, so normally we use the length of X, or the length of Y is preferably used because Y will be a vector. Okay, it will be a standard, so the length will be comfortable. So and then get item, you will specify which index that you want, that specific indexed item you will get it. Okay, it returns one element. Okay, so if I say that I want the element at index 20, now the 20th row will be returned, and then here the 20th element will be returned. Okay, this is how you create an instance of this data set. Now what is the length of this? Now the number of samples that you have got is 100. Okay, now you can go ahead and say that okay, I want 0th element. So whenever you are saying that I want 0th element, so you are actually making a call for this method get item, which is being defined in line number 16 and 17. You are returning the X value and then the Y value, as you can see, which is going into this sample X and sample Y, and then you can print it out. Okay, now this is creation of data set. Now the next thing is you have got a data set where in which you have 100 elements. Now you want to break them into batches. Okay, now because of see, these are 2-dimensional data, very easy to handle, but think of ImageNet wherein which each image is of size 224 cross 224 cross 3. Okay, so in that case we may not handle the whole bunch at the same time. No, in that case we want to make the examples into bring them into different batches. Now that is what is known as a data loader, creation of data loader. Now using this data set. Now what is the batch size? How many examples has to be there in each batch? I am saying that there has to be 16 examples in each batch. Now I have 100 examples. Now I have 16 examples in each batch. Now in the last one, now obviously there will be lesser value. Now as I told you, any model which is there is agnostic of the batch size. Okay, so now either you give 16 examples or you give 20 examples or you give 5 examples in one case, it is perfectly fine. It is batch size agnostic. Okay. Now then you see a very interesting thing in line number 8, which is shuffle is equal to true. Now what does this mean? What do you mean by this shuffle is equal to true? Now here, see, if you break your data set into batches of 16, 16, 16, okay, now let us say that you have broken it sequentially. Now what happens is first 16 example now will be there in the first batch. Now then index 1 to index 15 to 31 will be in the next batch. Now so on, if you divide it sequentially, every time the same order you will get the data in the same order. Now rather than that, what do? After each epoch you shuffle things. Okay, now so that the example that came in the first batch now may not come in the same batch. Okay, that is what this shuffle is equal to true means. Okay, so now you get data loader batch X and batch Y you work with, and each batch will have 16 examples because I have specified that the batch size is 16. Okay, this is how do you do it. Now this is a standard procedure, okay, that is used. Now the only data set modifies. Now if you are going ahead with MNest, now we will be using the data set for MNest. If you are using CFAR10, you will be going ahead with the data for CFAR10. Okay, so now let us go ahead and create an MLP for binary classification. Okay, now here I am keeping this agnostic with respect to the input size and then the number of classes. The only thing that I am doing it here is, okay, now the network that I am doing is, so now I have some x, okay, that I am multiplying it by W1, which is a matrix, plus B1, this is one transformation, this I am using some activation, okay, this I am multiplying with W2 plus B2 which is there, this I am passing it through, again same or different activation is perfectly fine, this I am multiplying it by W3 plus B3, okay. Either in the last time whether you pass it through activation or not, it is since it is a classification, normally we do not pass it through any activation in this case. This is what I am doing here. So now what is being done here, you need to declare W1 you have to declare it as some specific sized matrix, W2 and W3, and B1, B2, B3 you will be depending on the declaration of W1, W2, W3 it will be there. Now so if you want to think of it as this is the first transformation, this is applying W1, this is applying W2, and this is applying W3. This is the network structure that you are going ahead. Now here when I put 3 dots, I do not mean there are 3 nodes, okay, just for referencing I am putting it, okay. So now here, now this is the input dimension, this is the number of classes, okay. Now these two are fixed. Now depending on your data, your input dimension and the number of classes will be fixed. I am going ahead with a simple classification task, okay. So and then you have choices for this. Now this is the hidden dimension 1, hidden dimension 2. Now you can go ahead and go ahead with your choices, it is perfectly fine, okay. Now here the network structure that we have is, now I am creating an MLP which is a child of this NN dot module that you have. So the init method, input dimension, hidden dimension and number of classes. So the first I am going ahead and creating FC1, the fully connected, FC is fully connected 1, which is NN dot linear with input dimension and hidden dimension. Now this is W1, creation of W1, and then here FC2 which is hidden dimension and hidden dimension. So that means that I am choosing that the dimension of this and the dimension of this I am fixing it to be same, okay. It is a design choice that I am making, not necessary, okay. So in this case I am doing it, it can be different, and then I have NN dot linear, hidden dimension to number of classes, okay. And then how do we go ahead with the forward method? Now first you go ahead and pass it through FC1 and then pass it through ReLU and then pass it through FC2, then pass it through ReLU and then pass it through FC3. So now here this is exactly the same. First you pass it through this is you are passing it through FC1 and this you are fixing it as ReLU, and then whatever is there you are passing it through FC2, again this is ReLU of it. Now then this whole thing you are this whole thing whatever is the output that you are passing it through, this is FC3, okay. This is what is being done here, fine, good. So now here I am saying that the input dimension is 2, the hidden dimension is 32, so the number of classes is 2, okay. Now once you have number of classes is equal to 2, so you can have it as only one node, that is fine, one node or two node, it is perfectly fine, no problem. So input dimension is 2, now this is 32, this is 32, this is 2. Now that means that I have a matrix which is 2 cross 32, 32 cross 32 and then 32 cross 2. So this is the first matrix which has 64 element, this is 32 square elements, again I have 64 elements. So in total, and then now I have 64 plus 64 plus 32 square. Now these are the weights that are there to this plus I have 32 plus 32 plus 2, which are bias term for each one of the nodes. Now these are the number of parameters that are there, and then you want to go ahead and find the gradient with respect to each of these parameters and then update. Okay, fine. So now this is you are creating the instance of it, and immediately you are moving it onto the device. Okay, you are moving it onto the device, the CUDA device that you have, and then you can print the model. Now you can get it. Now then go ahead and train the MLP, the simple data set that we have declared. You have 2 columns. Y is the sum of, so if the sum is greater than 0, then it is 1, else it is 0. And then you have created a data loader, you have created an instance. So you are using cross entropy loss, it is a binary classification problem. You could have sufficed with only one node, and then you could have used BCE loss also, perfectly fine. There is another way of doing it. Here you are using the Adam optimizer. The optimizer that you are using here is Adam, and then you are using the same optimizer for all the parameters, and then the learning rate that you are using it 0.001. The number of epochs that I am going ahead with 20. Okay, so and then I am going with 20 epochs. So model dot train. Now here you are specifically saying that there are 2 modes of evaluation always. Now one is the training mode which is there, the other is the evaluation mode. Now model dot train will explicitly say that now the model is in the training mode. Okay, so the total loss is 0, correct is equal to 0, total is equal to 0. Okay, so this correct is how many of them are correctly classified. Now this total is how many examples are there. So just to compute the accuracy, number of correctly classified examples divided by total number of examples, because of which you can get the accuracy. Fine, good. So now you have batch. So this is what I told you. So please remember, in my earlier cell I have already made the model which is there, the neural network which is there, I have ported it on to the device which is the CUDA device. Now the X and Y which is there, which I am getting, also needs to be ported. Okay, by default the device that will be there will always be a CPU device. Okay, now that is what you are doing in line number 30 and line number 31. You are porting this X and Y onto the device. Okay, and then you perform the forward propagation through this. So you pass the X, you get the logits, and then now please remember, whenever you are CCE loss, for the loss the input is logits. So you do not need to explicitly apply softmax. Okay, so you apply the logits, and then the actual vector of labels. Okay, you are not converting it again into one hot encoding. Okay, no need for that. So and then you go ahead and clear off all the previous gradients, loss dot backward computation of gradients, optimizer dot step, you are updating the parameters. Okay, and then the total loss is whatever the loss that you have computed. So you are just incrementing it for each, you are just incrementing it, and then so what is the prediction? How do you get the prediction? So now this output will be a 2-dimensional vector. So the Y, okay, I will just put it here. Okay, the Y that I have now belongs to R2. Okay, now what it will be? Now this is Y0 and Y1. Now what is this Y0? This is probability that Y belongs to class 0 given X is equal to whatever specific X that I have. This Y1 is probability that Y is equal to 1 given X is equal to X, and you add, you should get 1. Okay, so now which is the label? Okay, now this is of index 0, this is of index 1. Okay, and please remember there will be a transpose of this will be a row. Okay, that is why you are using dimension as 1. So I normally prefer to write it as a vector, so that is the normal notation that is being used, so that it is easy for you to go ahead and comprehend. Okay, so now you take the maximum of it. Now if you take the maximum of it, you get the probability, you do not get the decision. Now whatever is the maximum, you want to find the argument pertaining to it. Okay, if Y0 is maximum, now what is the argument pertaining to it? It is 0. Okay, what is the index? What do you mean by argument is, I mean index in this case. Okay, so now which is 0. Now similarly for Y1. Okay, so you take the maximum, you compute the maximum element, and then you compute the what do you call the argument of it. Okay. Now that is this line here in line number 43. Okay. You got your predictions, and then how many of them are correct? Now how do you do it? Now you have your predictions, you are checking this is prediction will be it will be a row vector, your batch y is also a row vector. So you are saying that you are comparing these two vectors, okay, are they same? So now since you are going ahead with the relational operation, the outcome will be a Boolean vector. So and then you take the sum of it. Now that means that whenever you take the sum of it, what will happen is it will be converted into true will be converted to 1 and false will be converted to 0. So that will give you how many of them are correctly classified. Now whenever you take the sum, it will say how many ones are there, okay. So which is nothing but now how many in that specific batch, how many of them are being correctly classified, okay, and dot item, so that you are converted it into a value. So you increment the correct, and then this is the batch size of the size 0 of it, okay. Now size will give you a tuple, now you take the 0th element of it and then you compute the total accuracy and then do it. Now as you can see here, initially the accuracy was 50-50 and then it increased. So you can see that after around 15th epoch, now you can see that the accuracy is around 0.98, okay. So you can now get it like this, okay. This is how we work with the MLP, okay. Now this is where we conclude this segment of our tutorials. In the next segment, now we will see how we can work with CNNs in a similar fashion, how we can work with CNNs, how we can work with RNNs, and then we will declare CNNs and RNNs, we will make a networks out of it, and then we will see the propagation. That is what we will be doing in the next segment of the tutorial, okay. This is where we stop. Thank you, hope you enjoyed the tutorials. Meet you in the next segment, which we will be discussing CNNs and RNNs. Thank you.